Antimatter, the ultimate superweapon, the most efficient energy source, the most powerful and mysterious substance known to science fiction. Except, it's not fiction, it's reality. Hello, my name is Armand, and welcome to Simply Space. Today, antimatter. Antimatter was first theorized in 1928 by English physicist Paul Dirac. He proposed the idea by famously referencing the equation x squared is equal to 4. He drew attention to the fact that the equation had two solutions for x. One where x is equal to 2, and one where x is equal to negative 2. While this may not seem like a very significant discovery, the true brilliance lies in how these numbers relate to the very structure of our universe. The theory is that if x has two solutions, being 2 and negative 2, one positive and one negative, then perhaps matter works the same way. The idea is that maybe matter has a counterpart, and this counterpart became known as antimatter. But what is antimatter? First and foremost, it's important to understand that antimatter, like matter, is not just one substance but a collection of subatomic particles. These antimatter particles are almost completely identical to normal matter particles, with the only known difference being that antimatter particles have opposite charges. For example, we know that the electron is an incredibly small particle that has a negative charge of 1.602 times 10 to the negative 19th coulombs. The positron, which is the electron's antimatter counterpart, is also a small particle, but it instead has a positive charge of 1.602 times 10 to the negative 19th coulombs. Similarly, the antiproton has the same charge in coulombs as the proton, but its charge is negative instead of positive. In addition to that, all 6 quarks, along with every other particle in the Standard Model, have corresponding antiparticles with opposite charges. Now, it may seem, with matter and antimatter being so similar, that it's not as dangerous as it's often perceived to be. However, that is the one thing that the media has portrayed correctly about antimatter. When even the smallest amount of particles of antimatter come into contact with any form of matter, they both immediately destroy each other and release high energy gamma rays in a process that's formally known as annihilation. Wait, they destroy each other? You heard that correctly. They transform each other into small bursts of energy. But what about the law of conservation of matter? You know, the one about how matter can't be created nor destroyed? Well, technically that's not true. But in the grand scheme of things, the law still applies, since we have no means of accessing large enough amounts of antimatter to make a difference in the amount of matter that already exists in the universe. However, subatomic scale reactions between matter and antimatter take place multiple times every single second. At any given moment, a particle of mass, like an electron, pops into existence with an antiparticle counterpart simultaneously. And just after they appear, they collide and annihilate into gamma rays. This phenomenon is often referred to as matter-antimatter pair production, and it occurs when large amounts of energy are concentrated into an impossibly small area. While making pairs of matter and antimatter may seem like a newfound concept, you've more than likely heard about it before in a way that you may not have realized. Albert Einstein's famous equation, E equals mc squared, is the formula that breaks down this idea. Now, what it explains is that energy and matter are one and the same, and that small amounts of matter have incredibly high levels of energy that they can be converted into. In this equation, E is the variable that stands for energy, while m and c stand for mass and the speed of light, respectively. So, what does the speed of light have to do with energy and mass? Well, it acts as a constant, a massive number that shows just how much energy one could extract from such a paltry amount of matter. The speed of light is already a sizable number on its own, 186,282 miles per second to be exact. But the equation calls for the speed of light squared, which is far more vast in size. To relate this Back to antimatter, the amount of energy produced from an annihilation is twice the mass of the matter in the collision times the numerical value of the speed of light squared. And to facilitate matter-antimatter pair production, you'll need to concentrate enough joules of energy that is equal to the mass of the pair particles combined times the numerical constant of the speed of light squared. In addition to pair production, antimatter is released as a form of radioactive decay from the naturally occurring potassium-40 isotope. In fact, the average human body emits roughly 180 positrons per hour because of it. Thankfully, that amount of antimatter is not nearly large enough to cause any noticeable damage to our bodies. But even though we don't know all that much about antimatter, it does still have some practical usage in today's society. The PET scan is perhaps the most well-known and useful of these things. Now, the PET in PET scan is actually an acronym that stands for positron emission tomography. In a nutshell, PET scans send a few unstable molecules that release positrons as radioactive decay into the body. These molecules, known as tracers, are forced to become unstable shortly before the process begins due to their quick rate of decay and short half-life. Once inside the patient's body, the tracer decays and releases positrons that annihilate with a few atoms of internal organs. The annihilations send off two powerful gamma rays that move in opposite directions. The gamma rays that are released are then picked up by a detector that lies around the patient's body. From the gamma rays, a three-dimensional map of a specific area of the patient's body, which is usually the brain, is mapped out via triangulation. This 3D imaging process can help scientists with identifying and treating certain diseases such as cancer. Despite its ability to be used in medical practices, scientists are still mostly in the dark when it comes to antimatter. There are a few important questions that still need to be answered before antimatter can be fully understood. For example, could a planet made of antimatter exist? It seems to behave similarly to normal matter, but the real answer is still uncertain. If this hypothetical planet of antimatter existed in a universe full of antimatter, what would it look like? Would all four of the fundamental forces still work the same? Would things fall up instead of down? Would every color appear as its inverse? Again, no one really knows for sure. But there is one more question that has been boggling the brains of scientists for decades. Why is there so little antimatter in the universe? If matter and antimatter are always created in pairs, then why is there a significantly larger quantity of matter as opposed to antimatter in the universe? Obviously, the answer is uncertain, but some scientists have theorized that something must have destroyed the antimatter in the earliest stages of the Big Bang, and they have been working hard to discover whatever that thing might be. But if anything is for certain about antimatter, it's that we are thankful that we can coexist with it. Thanks for watching.